In this video lecture, we're going to talk about what happens when you put a charge in a magnetic field. Here we have a magnetic field that's pointing up and a charge that is initially stationary. The charge, because it's stationary, will feel no magnetic field. If you give it the charge some velocity so that it's moving also up with the magnetic field like this, it turns out it too feels no force from the magnetic field. It's only when you give the charge a velocity that is not parallel to the magnetic field that you would see a force due to the magnetic field. So it turns out that the magnetic force will depend on four things. First, it'll depend on the amount of charge that is there, Q. Then it'll depend on the strength of the magnetic field, B. Next, it'll depend on the speed of the charged particle. And finally, it'll depend on the direction the charge is moving relative to the magnetic field. All of these things can be summarized by the following general equation. The magnetic force is equal to Q times V cross B. This is the cross product. We've seen this before for torque, where torque was equal to R cross F. So like torque, the magnetic force will always be perpendicular to V and B, and it is maximum when V and B are perpendicular to each other. Let's look at the direction of F sub B more closely. As we said before, the direction will always be perpendicular to both B and V. To find exactly what direction it will be, you'll have to use the right-hand rule. We've seen this right-hand rule before when we were looking for torque in 201. To refresh your memory on what the right-hand rule is, what you do is you would put your fingers along the direction of V, the first vector, and then curl your fingers towards B, the second vector. Your thumb will then be pointing in the direction of the force. Now, sometimes because B, depending on where V is pointing, you cannot curl your fingers, and the only way to be able to curl your finger is to flip your whole hand, in which case your thumb will then be pointing down. If you're a little rusty on how to use the right-hand rule, don't worry, we'll get more practice in class. Now, the only thing different between the right-hand rule for magnetic field and torque is that sometimes the force is opposite to the direction you find, and that's because of the charge. If you're doing with a negative charge, because it's negative, the force will give you a minus sign, and it's opposite to the direction of your thumb. If it's a positive charge, then there's no problem. It's the same direction as your thumb. Now let's talk about the magnitude of F sub B. So if you have a magnetic field going in one direction and the velocity is going in another direction, and you're given the angle theta between them, then there's a simple equation that will give you the magnitude. Here, the magnitude is equal to Q times V times B times the sine of theta. Now, let's suppose that you weren't given the angle between the two vectors. There would be a simpler way if you knew how to break down the velocity components, because what matters is the perpendicular component of each vector relative to the other vector. So, for instance, the velocity vector here can be broken down to two components, one that's parallel to B, V parallel, and another that's perpendicular to B, V perpendicular. What matters in the magnitude of the cross product is the perpendicular component, V sub B. So the equation becomes simply V perpendicular times B. We can also look at the components of the B field. There's going to be, if you break down the B field, there's going to be a component that's parallel to V and a component that's perpendicular to V. And this is the component that matters when you want to find the magnitude of the cross product. So in this case, the magnitude would be equal to v times b perpendicular. So let's do an example. Here we have an electron that's moving through a constant magnetic field given by b vector equals bx in the x direction plus 3bx in the y direction. So we don't know this bx. The electron has a velocity of 2 meters per second in the x direction plus 4 meters per second in the y direction, and this produces a magnetic force acting on it of 6.4 times 10 to the minus 19 newtons in the z-hat direction. And we can write it like this. Now this problem can be done several ways. One very simple way is if we knew how to do the v cross b using cofactor expansion, we can easily get the answer. But let's not do that because we want to illustrate some of the things we were saying before. Namely, we want to use the formula for the magnetic field, for the magnitude of the magnetic field, QVB times sine theta. Here, since since an electron, Q is going to be minus E, and then we multiply by V times B, and then times sine theta. V is the magnitude of the velocity, so we can write it down quickly. The magnitude is the square root of Vx squared plus Vy squared, and it turns out it's going to be, if you put it in the numbers, it's going to be root 20 times meters per second. The magnitude of the B field can be written the same way. It's going to be square root of Bx squared plus By squared, and putting in the values for the x and y components, it's going to become root 10 times b sub x. Now, we don't know this angle between the two, between v and b. We don't know theta. But we can find theta if we knew the angle each vector makes with the x-axis, namely the angle that v is making with the x-axis and the angle b is making with the x-axis. So let's find the angle that v makes with the x-axis, and let's call this angle alpha. To find alpha, we just use trigonometry, because tangent of alpha is going to be equal to Vy over Vx. And putting in the numbers for Vy and Vx, tangent alpha is going to equal 2. Solving for alpha is going to be 63.4 degrees. So this is the angle V makes with the x-axis. Similarly, we can try to find the angle that B makes with the x-axis. The angle here, let's call it beta, and the tangent beta is going to equal By over Bx. Also putting in for By and Bx, remember By is equal to 3Bx over Bx, it's going to equal 3, which then gives us beta equals 71.6 degrees. So by knowing both of these angles, we can find theta, because theta is simply going to be beta minus alpha. So subtracting the two angles, theta is going to equal 8.2 degrees. Now we're ready to put everything into the equation. For f sub b, putting in the numbers, we'll get this expression here, which will allow us to solve for b sub x. And it turns out the b sub x is equal to minus 2.0 Tesla. And that's our answer.